I think we'll go ahead and get started. Thank you, everyone who's able to join in person today. Thanks, folks, as well, who are able to join virtually on Zoom. I am beyond ecstatic to welcome, you can see from the grin on my face, friend and colleague, Dr. Martin Chapman. Dr. Chapman has his Bachelor of Science in Potions from Hogwarts University. No, Martin had to know that I was going to throw at least one Harry Potter joke in there. Don't ask him if he knows Harry Potter. British people hate that. I found it. No, Dr. Chapman, very serious now, has his Bachelor in Science in Computing from the University of Liverpool. He's got his PhD in Computer Science from King's College London. And since getting his PhD there, and that was in the computer science group, but he's transferred over to the informatics department. He's currently a lecturer in health informatics at King's College. I describe him as a biomedical informatician, but also as a research software engineer, given his background in computer science and development, which I think is a wonderful and beautiful, mashing of skills to see in the informatics field. He's done a lot of great things, and I promised I would keep it short because nobody's here to hear me talk. Some of the work that he's accomplished has been around decision support, artificial intelligence and simulation. And a lot of the work that he's renowned internationally for is the formalization of patient cohort definitions, which we also call computable phenotypes, phenotype algorithms, things like that. You might have heard those terms. And his foundational work with the Phenoflow system that you're going to hear about is an underpinning of the HDR UK's National Phenomics Resource, which is the UK's first national phenotype repository. So I could keep going on, but I'm going to stop there and give you plenty of time. So again, welcome, Dr. Chapman.
Thank you so much, Luke. When I was preparing this talk, I was going to put a picture of our campus on the slides, which does look a little bit like Hogwarts. But I was scared of doing so in case it caused jokes, but clearly the jokes were ready anyway, so I might as well have just gone ahead and done it. Thank you for such a nice introduction. It's really lovely to be here. I know it's a complex time in the world and a complex time in the US, but it's always such a pleasure to come here, especially to Chicago, because there's so many people here that I've loved working with, some for many, many, many years. I am, as you can tell, and as Lucas said, from the jokes and from the accent from across the pond. I'm from London, originally from the north of England, but now in London, from King's College, London. Somewhere that you would be very, very welcome to visit anytime. We've got a lovely Hogwarts-esque campus, as per my previous joke. So what am I gonna talk about today? So the title we have is Phenoflow, an architecture for fairer phenotypes. What I want to talk about is computable phenotyping, EHR-based phenotyping. We'll make that kind of distinction a little bit later. And if you're here, you probably know what that already means. But I will go through that again, just with a very simple example. I'm going to kind of talk about the architecture or the environment, or more appropriate to say the environment that we have at the moment in the phenotyping space, what things look like now, what the problems are, particularly in terms of the computable forms of the phenotypes that we have. And I'm going to talk a little bit about potential solutions to that. We're going to talk about needing a model for phenotypes. And then I'm going to move on and talk about one particular model, which from your title you probably guessed is called Phenoflow. I'm going to talk about the conceptual and theoretical contributions of Phenoflow, and then a little bit more about the technical contributions of Phenoflow. Because as Luke has said, I consider myself a bit of a software engineer and a researcher. Okay, so an architecture for fairer phenotypes. One thing I want to make clear is I'm not here to sell Phenoflow as a product. I'm not here to say Phenoflow is this amazing thing. You please use it. I mean, please do use it, but I'm not here to kind of sell it to you. I'm here to more talk about the questions and problems that Phenoflow or our work on Phenoflow has shown us, and how, to be honest, we've not been able to solve all of them. There's still lots of outstanding problems. Phenoflow is far from perfect. So I want you to bear that in mind. If it turns into a sales pitch, that's not my intention. And towards the end, I'll try and dedicate some time to talking about its limitations, which I think is really, really important as well. Okay, so a bit more formal, what am I going to talk about? So just to summarize what I've said, I'm going to start with some definitions for those who might not have be familiar with the space. Talk about the phenotype landscape, models, architectures, and then the future, everything that I've just said. So starting with definitions, what's a good thing to start by defining? Well, probably me. probably good to define who is Martin Chapman, how do we define me with the dramatic mic clip as well. I'm going to show you a diagram, and Luke has kind of summarized it really nicely already, but I call this my 3 a.m. diagram because at 3 a.m. in the morning last year, I woke up and I realized I had no succinct way to summarize my research, and that stressed me out. Because probably like many people here, I work on lots of different areas, and there's real pressure now to sell ourselves as working in a certain area. But it's quite nice to resist that in a way. It's quite nice to move between different areas, but I thought I need some way to summarize this. So this was my 3 a.m. diagram. I hastily constructed this in pen and paper and then ended up making it a bit smarter later on, as you can see here. So what this really shows and summarizes, again, to the goal of summarizing or defining who I am and why I'm here and what I'm talking about, is the areas that I'm interested in. So I'm interested in a variety of areas. I'm interested in AI-based simulation, agent-based modeling to understand population health problems. I'm interested in computable guidelines, making these rules or guides that we have for clinicians computable and working with those. I'm interested in much more of a kind of software engineering space in terms of sensor-based clinical decision support systems. How can we define data streams together? And then most pertinently for this talk, I'm interested in computable phenotyping. And so a nice way, I hope, as per my 3 a.m. ramblings in my mind, to summarize this is these all feed into decision-making. So if you're asking what area do I work in, I say I work in decision support in healthcare. All of these, as you can hopefully see, feed into decision-making. Why do I run a simulation? Well, because I want to make some decision. Why do I use computable phenotypes? Well, because I want to understand who has what disease, who doesn't have that disease, and that then helps inform my decision-making. So that's how I'd summarize myself. There's a few takeaways from this. The first is that you can see there's a lot of computer sciencey stuff here. I'm not a clinician. I've been working in the health informatics space for about 10-ish years, so I've picked up the jargon, but I'll never be a clinician, so bear with me. Also, again, as Lucas very kindly said, I don't really consider myself a traditional researcher. Software engineering really guides my work, and it's lovely that communities have risen up both in the UK and the US to support this kind of work, the RSE communities, and that's really something that I consider myself a part of. And then finally, what else to take away from this? Well, as I've kind of said, phenotyping is a significant part of the work that I do. Okay. But continuing with definitions, and I know there's a lot of people probably working in this space. I know there's a lot of people working in this space in the room, so I don't want to cause any upset, but I'm going to try and succinctly summarize what EHR-based phenotyping is in a single sentence, which is tricky. And I've given a little disclaimer there that this is just my take for this context. So we have my work. Part of it is EHR-based phenotyping. What is it? Well, broadly, I would say it's the logic required. I'm going to stick to the script. The logic required to identify individuals with a disease or condition from their electronic health/medical records. That's the terminology across the pond, I think, alone. So how can I automatically identify from these huge sets of data, this big data that we have, you might call it, in terms of health records, how can I automatically identify who has which disease or condition? And I add the condition bit on the end intentionally because we're not just looking at diseases. We can have phenotypes for things like, at least in our UK libraries, things like homelessness. So there's a really broad kind of definition, so to speak, for what's covered, what we're actually trying to automatically identify. So we start with me, defining me. This is the space in which I work. Phenotyping, this is what EHR-based phenotyping is. I'm going to use this kind of running example that I'm going to periodically come back to just to emphasize a very, very basic phenotype. And our phenotype actually consists of, and I now get to try out the pointer, which is pretty cool. Our phenotype consists of 2 codes, this 13AB.00, does that show? Yeah. And another code here, 13AC.00. And these are actually codes, these are read codes related to diabetes, at least in a UK context, in the read code context. And then we have another code in the middle, which is not part of our phenotype, which I believe is for asthma, okay? So the simplest possible phenotype could consist of these 2 codes. And what we could basically say is, let's say we have 4 patients. 2 of those patients have the type 2 diabetes phenotype that we're interested in. They have those codes. 1 doesn't. So when it comes to ask who has type 2 diabetes, I'm going to abbreviate to T2DM. Then patient 1 has diabetes as per this phenotype, and patient 3 has diabetes as per this phenotype. So those of you who work in this space are probably already screaming at this. You know, there's so much more nuance here. I get that, totally, completely agree. But I'm going to anchor, just for the sake of this talk, to this very, very simple idea that if you have the code, you have the condition. I'm going to add a little bit of nuance, because I'm not saying if you don't have the code, you don't have the condition. So I'm adding a little bit of subtlety there with my hyphens. But basically, this is how I'm going to define diabetes or phenotyping as a whole for EHR-based phenotyping for the purpose of this talk. I'm going to add in a little bit more complexity, which may again cause a bit more controversy for those in the room who are familiar with this space, but just again to help us conceptualize things. Something I like to do is I like to split so we have EHR-based phenotyping as a whole kind of approach. And within that, I like to say there's two different types of entities. There's what I'm going to call, or what I like to call, the phenotype definition. This is what I call the non-computable logic. And I know that will align with some terminology others use and perhaps not with others. And that'll be what we've just seen, right? You can't, oh, going the wrong way. You can't execute this table, right? You can't take this table and run it in a computer. It's just symbols, it's text on a screen. So this, but it does communicate the logic of the phenotype. Whereas in the examples that we'll see later, we can have different forms of this logic that's actually implemented and can run on a computer. Yeah, this is what I'm going to call the computable phenotype. That makes sense. So we have, at least for this terminology, for the terminology I'll be using, we have the definition, not computable, and then we have the actual implementation of that logic, the computable phenotype. And again, if this is contentious, I apologize. If this is really, really familiar, I also apologize, but that's just to bring us all onto the same page. I know there's some FAIR fanatics, shall we say, in the room, people who love FAIR. And I'm going to apologize that I'm absolutely not going to do this justice in a single slide. This is such an important area. It's such an important thing to have. I've had conversations very recently in the last 10 minutes about how this should be a part of everything that we're doing. It absolutely should be. So again, I'm not going to do it justice, but just again, for the sake of the time that I have, we can summarize as a part of our definitions what FAIR means is effectively promoting reusability, right? It's actually way more nuanced than that. It's got all these components as per the acronym, findable. You have to be able to find your research objects, things like phenotypes. You need to be able to access them, and you need to be able to, they should be interoperable. But at the end of the day, as per the little orange arrow there, I think what this all distills down to is reusability. So when, and what you might have noticed I'm doing here is kind of defining the terms from my title. When I say FAIR phenotypes, it's not just nice verbal alliteration. What I'm saying is we want to have reusable phenotypes. And what we're going to try, or what I'm going to look at throughout the next few minutes is why this actually isn't the case sometimes, how it could be the case, how we could have fairer phenotypes, and how Phenoflow, the technology we've developed, the model we've developed, might help us move more towards that space. Okay, does that make sense? Please feel free to jump in at any point with questions. I'm very, very happy to talk. I like to take an informal approach to these things. So how do things look right now? And bearing in mind this separation between the definition and the computable form, in terms of the definition, we're actually, I think, in pretty good shape. Not entirely true, but at least compared to the computable forms, as we'll look at in a second, we're in pretty good shape. So those of you who work in the phenotyping space will have almost definitely, I guess, heard of Cypher, which was kind of the, I think things like PhKB walked so that Cypher could run, or whatever the phrase is, because I know it's obviously emerging from, no pun intended, from other initiatives. And then we have the kind of UK equivalent to this, which is the HDR UK Phenotype Library. And what these are, as the name suggests, is these huge collections of phenotype definitions. They capture at scale the logic for these definitions. And the key thing, as we'll look at in a moment, is they're not computable directly. Remember, it's just, you couldn't take this page and run it. There's no computable form. So why is this a good thing in terms of fairness? Well, it's nice because, as you can see here from the examples that I've shown here, these libraries, they enforce a certain structure to the definitions that you host. If you host a definition in the HDR UK Phenotype Library, which we've done a lot of work with and we're a big part of, you have to, for example, specify the data source that your phenotype was written against. And the same, I believe, is true in Cypher as well. So we're actually in fairly decent shape. We're in decent shape in terms of the fairness at the definition level of phenotypes. There are other problems with these libraries, but at least for the argument for this lecture, we'd say we're in actually fairly decent shape, where these definitions go a long way. Having them in this standard structure goes a long way towards ensuring reusability by things like having the data source there specified. Okay, so that's the definition landscape broadly. And again, I'm oversimplifying, but again, just for the sake of this lecture, we're in okay shape there. So as I've said, there's a difference between the definition and the computable form. And in many ways, these libraries kind of ignore the computable form. I can't go onto the HDR UK library, well, you couldn't before we came along, and execute those definitions directly. And that's not good, right? We shouldn't be ignoring the computable forms of these definitions. We shouldn't just be saying, oh, I've got my code list, it's on Cypher, I'm done, everything's okay. Because out there is this huge corpus of code, of computable phenotypes, of examples of where individuals, where research teams or institutions have built computable forms of these definitions. They're out there, and we shouldn't ignore them. Why shouldn't we ignore them? Well, because it improves, and again, this might be a contentious terminology, it improves what I like to call phenotype portability. If someone has already done the work of implementing your definition, then that's much less work for you to come along and then use that elsewhere, in theory. But again, at its core, I think and hope that principle holds. So you might say, great, there's got all these lovely Python versions of my type 2 diabetes phenotype. They're out there. Let's just upload them to the HDR library. Let's make them available for download. Let's take my ad hoc Python scripts and make them available. If you were to do that, I would argue that that would really compromise the fairness, the existing fairness we have at the definition level in these libraries. At the moment, remember, my argument is things are fairly good. We've got this nice structure to the definition. I would say if we recognize, yes, there's a problem in terms of not having these computable forms, but we just go ahead, blindly upload them, that's going to not be good. That will compromise the fairness of these definitions. And why is that? Well, basically, because some of these implementations are really bad. And they're really bad for a number of reasons. And later on, you'll see how I map this to a few ideas around modeling. One of these things these definitions tend to do, and I've modified this from the original example, but this is a semi-real example from GitHub, is that people hard code in the logic into their Python script. They assume that the Python script is the phenotype. This is not right. That's not how it should be. We lose this very important distinction between the abstract layer, between the logic and the actual realization. And one way they do that is in comments. So here, for example, we've got this little Python script, which again uses the codes that I showed you at the beginning. It does something very, very simple. It's probably not perfect Python. It's more pseudocode than anything. It will read in a CSV. It will go through the lines in the CSV and check, does this patient, who we assume is in the CSV of patient data, have these codes? And what the author's done here is they've actually directly embedded information about the logic in comments. And that's not good. I don't think that's nice because it makes things much more complicated. It makes things much more difficult to follow. Like, what does this mean, hard code the criteria? What criteria? What does this mean, find case patients? What's your definition of a case? And again, and I'm going to keep relating this back to fairness, when that happens, when you conflate these two things, when you conflate the logic with the implementation, as has been done here, you reduce intelligibility, much harder to read. If it's harder to read, people just aren't going to reuse it. Okay? So this is kind of problem one. Problem one, if I take the phenotypes that we already have, the computable phenotypes, and just upload them, problem one. What else is bad about the definition landscape? This one actually isn't bad. It's just sort of a product of the way things go. I think most of you in this room, if you've worked in the computable phenotyping space, have probably used more than one language for your computable phenotype. Many people have probably used Python. Some people might have used R, don't know why, but you might have done. And some of you might, no offense to anyone in the room who might love R, and some of you might have even used SQL, right? This is kind of wonderful. This is how things should be. You should be able to leverage the different benefits of different languages for your use case. However, for fairness, it's bad because if you have 16 different versions of your implementation, then it all again just becomes very confusing, becomes very inconsistent, and it becomes very, very hard to reuse things. Which version do I use? What works? What was this for? How does this differ? How does this Python implementation differ from this SQL implementation, for example? So a little example there of this sort of state that I'm discussing. So we started with our Python script from our previous example, and we imagine someone has come in and then written an SQL version of that. Okay, so that's problem two. Problem one was things were kind of unintelligible. We'd mashed together the logic with the implementation. Problem two, which isn't really a problem, it's actually quite nice, lots of different types of implementation. And then problem three is that, code is kind of complex, right? It can get kind of complex. It can get worse than that. It can get quite idiomatic. People have ways of writing code that won't make sense to other people. I've just chucked in this line. This is some regular expression I wrote 2 years ago. I've got no idea what it does. I can't remember. It just looks complicated. I'm sure it did something at the time. This problem, I hope neatly illustrates that problem, that the third problem here of computable phenotypes is this complexity. If you don't have some kind of description of the logic, stuff is going to get lost. It's going to become complex, idiomatic, and really hard then, again, to reuse. And again, I appreciate that I'm in some ways butchering fairness by saying it's all just reusability, but that's what I'm going to simplify for today. Finally, and again, probably a nice big one here is when people write these implementations, when you write your Python script, you're probably plugging it into a single data source, right? And that data source is probably OMOP, let's be honest. But the problem with OMOP, as wonderful as it is it's not yet ubiquitous. Yeah. So and this example here, again, mostly pseudocode, I'm imagining that I'm at some point in my process, I'm calling an OMOP endpoint and reading in my data, and then later on coming along and analyzing that data. So what I've done here effectively is I've tied my implementation to a single standard. So if you aren't using OMOP, you're actually not in a great place in terms of reusing this computable phenotype. You're going to have to do some extra work that maybe you don't want to do, and it again affects things like portability. Okay, so these are our problems. This is our landscape. We're doing pretty well at the definition level, and there's work going on at the implementation level, but it's a bit ad hoc. And if we try and combine these two worlds together, we're going to get problems. Why is that? Well, because of the way that the implementation and the logic are combined, because of the different languages people are using, and because of the complexity of the implementations, and finally, because people tend to tie things to the same standard, okay? That makes sense? All right, yeah, good. Everyone understand my British accent? Sound good? Yes, good. Excellent, okay. So I've laid out the problems. I've hopefully defined a few things, and you're all okay broadly with the terms. I've laid out some problems. I'm now going to talk a bit about potential solutions. I'm going to lay out some requirements for a solution, is probably a better thing to say. And I'm going to do that by introducing something called phenotype models. So again, if you're here, you probably know what a model is. But if you don't, I'm going to use a slide that I love from my my master's course, where I also talk about models and introduce the concept of models to clinicians, for example. And why do I love this? Well, you can probably tell. That's because there's Lego here, and I have an unhealthy obsession with Lego. You'll also know that Lego is from Denmark. Lego is something that Denmark has looked after for a long time. Takes real pride in, but kind of lets it nurture and grow. And I'll stop there on the advice of the KCL lawyers. As a Danish citizen, though, I had to say something along those lines. What is modeling, though? So I like to tell students that, when you say the word model, they tend to think about models like Lego. And that's right. A model is really something, it captures something from the world, right? And people tend to think about models going in the kind of abstraction way. They tend to think about models as, well, I'm capturing something from the world so that I can achieve some goal. In this lecture, I like to say that imagine if I want to learn if a plane with these pontoons can float or sink, I might build a model and then test it in some water, test it in my bathtub. And if it sinks, I then learn something about the world, right? But people tend to think less about the modeling process going the other way in terms of the models actually being used to inform how we do stuff in the world. Now, obviously, you wouldn't build a real plane. You wouldn't follow this arrow and build a real plane from a Lego plane, but hopefully you can see the example that models, as well as capturing knowledge, can also be a template. It can tell you how to do something in the world. So when I talk about phenotype models, what I'm saying is that we need a template. We need a consistent template for how we define and build phenotypes, how we kind of structure phenotypes. And in many ways, again, we're doing that quite well at the definition level. So phenotype models, as I've said, they structure phenotype definitions. They govern exactly what should be in there. And again, at the definition level, as I was saying, we're doing quite well. And I would say we're doing quite well, as I alluded to before, because these libraries where these definitions live, they enforce that there should be some information there. They have what I would say is an inherent model. They might not be calling it that. They might call it a schema or something like that. But they are using a model for how phenotype should be, what data they should include. When people who have built the HDR-UK phenotype library say, well, part of what you need to include is your data source, what they're really saying is we have a model for a phenotype that includes having to specify what data source you've built against. And what I would say is that we can do the same thing at the computable level. We can actually come along and say, well, yes, we've got all these inherent models. Why not have an explicit model? Not one that we kind of just loosely use, but one we actually put out there and say, this is how you should specify your phenotypes. And let me lay out some requirements for these models that, interestingly enough, or hopefully helpfully enough, map to all the problems that I've just specified. So in terms of conflating the logic with the implementation, our model needs to have some connectivity between the phenotype definition and its computable form. It needs to allow them to link together, but at the same time, not anchor them together in the same way that the code here does. Again, coming back to our second problem, which was people using different languages, our model needs to accommodate and potentially combine, if necessary, different computable forms. We don't want to stop people writing in Python, people writing in R, people writing in SQL, but we need to somehow connect these together. We need to retain clarity. So again, remember this regular expression, this tricky regular expression. We need a model that allows us to specify exactly what's going on so that we can offset that. And finally, we need a model that supports a variety of target data formats. We don't just want to anchor ourselves to something like OMOP. We want some flexibility. And this is where, and again, I'm not trying to sell this. This is just our approach to this. It's thrown up, to be honest, a lot more problems than it probably solves, but that's part of the research project. That's why it's fun. To solve this, we introduced, or to try and solve this as a proposed solution, we introduced what we call Phenoflow. And Phenoflow is so called because it combines phenotypes, what we call workflow-based models. So if you've ever used something like KNIME, that is effectively what we're using here. What we're effectively saying is, we think phenotypes should be structured under this workflow-based model. And the specific model that we've derived this from is something called the Common Workflow Language, which you might have come across as well, where we effectively say your phenotype should be structured according to these set of steps, and these steps transition your cohort or your population through this logic to get your final phenotypic cohort. Does that make sense? So we're proposing this model called Phenoflow. It's so called because it's phenotypes under a workflow-based structure. And what does that structure look like? Well, it looks a little bit like this. It's not a perfect representation, but this is, I think, a good way to go to kind of look at things. This is an individual step of our proposed model for phenotypes, this Phenoflow model derived from the Common Workflow Language. And the key thing to take away is that we've got these individual layers. We've got layers now to our phenotype. One is this abstract layer, and the next is a functional layer, and then we have this computational layer. And then I've connected it in the diagram, but in reality, that's where the model stops and where the actual implementations then begin underneath it. Okay. So not expecting you to understand this straight away, lots of bits there, kind of small as well. But what I will kind of pull out is the different layers, because I think that's helpful to understand. So as we saw, we have this abstract layer, and this expresses the logic of the definition, and that's all it says. All this abstract layer says is kind of akin to the definition with no implementation. This is how the phenotype should run. In between that, we have this functional layer, which again is designed to help with clarity. It tells you what's coming into this step of the definition and what's coming out of it. And then finally, we have this computational layer, which starts to say more about how do I actually realize this logic? What do I need to do to actually build some units that execute this workflow that I have? And again, I don't want to claim complete originality here. This is heavily derived from the Common Workflow Language model. We spoke to the CWL team a lot about this. We've developed it in conjunction with them. They love that we're using it. We do say it's sort of a slight specialization on the CWL model in the sense that you can have, for example, an arbitrary ontology within your CWL model, controls the types of steps that you have, whereas we have a fixed ontology. Again, won't go into that for the sake of time, but there are variations. And if you want to learn more about that model itself, I'll elaborate a little bit more now, but more after the lecture, then there's a paper there authored with some wonderful people who are also in this room. So that's the Phenoflow model. And let me talk now a little bit about how it potentially solves those issues that I outlined at the beginning and how it potentially meets those requirements that I then put in place in the light of those limitations. So what you can hopefully see from this, and as I've kind of alluded to already, is we meet this kind of difficult kind of trade-off whereby the implementation is separate from the computable form, and we don't want to mash them together with comments, but there's still connectivity. Because of the layers, I've got a very, very clear abstract layer. I've got a very, very clear definition of logic, and also a very, very clear definition of what that implementation is going to look like. I've been able to specify here exactly what this step of my phenotype does, and therefore I've been able to connect it then to the implementation so they're together, but they're at the same time not together. That makes sense? So I've got this layered approach. There's connectivity between the layers, but they're also quite clearly separate. There's no real danger if, for example, if I'd taken everything from the abstract layer and just put it in comments, there's no real danger of the two being mixed together, which hopefully, or we think solves then that first problem around having these two linked together. Hopefully you can see, and as has been hinted to by the double boxes there, the beauty of this model, the beauty of CWL is you can plug and play your implementation bits. You can have this abstract logical description that's realized in multiple ways. You can plug in initially, for example, a Python implementation, and keeping that same abstract logic, you can then unplug that and then plug in an SQL definition instead. So again, this solves the problem of, yes, we've got different implementations, and originally it was kind of a bit unwieldy. Do I use the SQL? Do I use the Python? Here we're saying, well, actually, it doesn't matter. Use whatever you want. The abstract layer remains. The actual implementation, the computable realization, can actually just be what you want underneath the hood. Okay? So we're solving or trying to solve this problem of having these different computable forms. I won't talk too much about this because I don't think it's as pertinent for the type of simple definitions that we have here. But there's also a lot of beauty in having those self-contained implementation units, in the sense that when we build more complex definitions, things that use things like machine learning, we can very easily plug those in as well. Because remember, the abstract layer is agnostic to how this is actually achieved in practice on the computational layer. Again, won't say too much about that at this stage. So remember, our other problem was with this idea. Remember the regular expression that I couldn't even remember what it did? Hopefully you can see that now that we have all this information, in the abstract layers that we're enforcing being present, we really try and combat this issue of clarity. We actually specify in our model that you need to say 3 things about your logic. You need to give it an ID, you need to give it a summary for what it's designed to do. You need to elaborate on that summary, you need to give a description of the functionality. And then finally, you need to classify that step under a certain ontology. You need to give it some kind of classification. What type of step is it? What am I trying to achieve in this step? So there shouldn't be any regular expressions that remain undocumented, because you've documented all of this, hopefully, if you're following the Phenoflow model at the abstract layer. And the whole goal here then is to feed into this clarity. If things are clearer, as with all the other things, all the other benefits I've mentioned, if things are clearer, they're fairer, more reusable, and then we have this fairer phenotype landscape. Other things that help with clarity, inputs and outputs. Remember I mentioned at the kind of functional layer, this metadata that we have. And overall, having this logical flow to the phenotypes and having expected structure all feeds into clarity. It's all very helpful. So some of you are probably thinking, and I've had conversations to this effect just this very week, why is this nice? Why is this helpful, especially for simple use cases? Why do I need these steps? Why do I need steps when really I'm just doing one thing in my phenotype, which is, does this patient have any of the T2 DM codes? And you're absolutely right. For these simple use cases, it's probably less clear why having a step-by-step approach is important. Hopefully you can still see that even for the simple use cases, having the layers, having the connectivity, having the clarity is still important. But the steps is probably less clearer. And that's true. If you just have one main logic step, the need for steps is less important. We can introduce what we kind of call some artificial steps, where we might group some codes to create steps. But that is something that we've done. But again, that has revealed some problems that I'll talk about quickly if I have time at the end. So with the simple example that we've been following, hopefully you can see, or I agree, that maybe the need for steps is less important. But if you imagine more complex definitions, if we increase the complexity of our phenotype just slightly, so as to not just include one terminology, but include 2 terminologies, so not just read codes, but also SNOMED codes, then already hopefully you're starting to see how there's a sequential flow then to my phenotype, which I need to capture. It's still a little bit hard to justify, but again, think about some of the phenotypes you've worked with. Many of them are probably fairly sequential. They have branches, etc., which is, you need to have a code that falls within this state. You need to then have a different code from a different terminology that falls within that date. Your patient needs a certain age. There is a flow there, and that's what we're designed to capture. That's why I've been talking about steps. Another reason why I've been talking about steps, another reason why the Phenoflow model works with steps is to solve our final problem, which is this idea of target data formats. So I remember my final problem that I laid out was the fact that everyone sort of probably plugs into OMOP. That's not great, because then what if I'm not using OMOP? What the Phenoflow model allows me to do is to actually say, well, the first step in my workflow isn't going to be logic. It's going to be entirely assigned to reading data. It's going to be entirely designed to reading data from my data set, be it OMOP, be it I2B2, be it FHIR, et cetera, et cetera. And that's nice, because then if I want to use a different data set, I can effectively just chuck away that in that first, what we call connector. I can chuck it away and I can plug a different connector in, and I can then use that logic with different data sets. Because of this modularity, I retain the logic that I have in these intermediate steps, in these final steps, and I just change the first step, and then it will work beautifully, in theory, against different data sets. Does that make sense? Am I okay for time? I think I'm getting there. I'm doing okay. So that's the Phenoflow model. And again, I'm not trying to sell you a product. It feels a lot like I am, I know. I'm just selling you an idea for how to address some requirements, which I laid out in the second part, which in turn address some issues around the fairness of these objects. Okay. I'm going to talk very briefly, because I am a software developer at heart, about how do we actually realize this model? Because it's all very well having a model, but how do you get it out there? How do you get people to actually use it? You do not expect them just to build their own workflows. Well, absolutely not. So Phenoflow is both a theoretical model and also an architecture, a software architecture that one can spin up if one wanted to at an institution. And this is what it looks like. So again, I'm not going to go into many details right now, but I'll unpick a little bit of this architecture to explain what's going on here. But effectively, what we try and do with this software version of Phenoflow, this software architecture, hence the word architecture in the title, is we try and bring this model to the phenotyping space. We try and help make these benefits more broad in terms of phenotypes. And how do we do that? Well, someone reviewing this paper once said, our first Phenoflow paper, a model is only useful if it's used, right? It's all very well throwing out this model into the world and expecting people to use it. So how do you get around that? Well, you force them to use the model. You connect into their API, you ingest thousands and thousands of their phenotypes, and you standardize them. And that's exactly what we did. That's exactly what we do. We plug into APIs and we standardize their phenotypes. And what does this process look like? Again, I won't spend too long on this, but broadly what we do, and again, at the moment, and this is part of the limitations, we only do this for code lists because it turns out it's actually pretty hard to do. But for code lists, we will take the list, we will introduce, remember this arbitrary or kind of steps that we talked about, these artificial steps to kind of try and help a little bit with clarity. We'll generate implementation units, and then finally we'll spit out at the end this common workflow, language workflow. So this is what we do. We go to these libraries, we take their phenotypes in, we standardize them, and then we make them available for people to use. And I've said at the end there that we push things to GitHub. And you might be thinking that's a bit of a strange choice. Why not just use a traditional database? And again, you'd be right. It is a bit tricky using GitHub as a database, which is effectively what we do. But we get a ton of benefits from this, right? And again, just to unpick the architecture, GitHub or any other version control system, to be honest, we work with a few, is at the heart of this. Why is that good? Why do we dump our phenotypes once we've passed them to GitHub? Well, you're probably thinking that the benefits here are quite obvious. Version control. If you've written phenotypes, you've probably got hundreds and hundreds of versions of them. We need to be versioning them. And if you're dumping your original phenotype before it's even been used to GitHub, then you are setting a good precedent there. A persistent storage mechanism. If Phenoflow goes down, which if you've been to Phenoflow, kclhi.org/Phenoflow, you will see is the case right now. I'm giving a talk today at a prestigious US university on Phenoflow, and our dev team decided today was the day to do maintenance on our server. So unfortunately, Phenoflow is down right now, but because we're dumping everything to GitHub, which will never go down, it's still there. You can still access it. Okay, so this is a very pertinent point for why GitHub is good. Branching, again, I'll talk about this again in a second, and submodules are also two benefits of this approach. So let me give you, I've alluded to this already, but where have we been doing this? So I talked a lot about the HDR UK library, and I think Luke mentioned this at the beginning. We're hooked in massively with the HDR Phenomics Resource Initiative, and our role there is to do this standardization. We've ingested, quote unquote, something like over 1,000 definitions from the HDR UK phenotype library. We've standardized them, got rid of all those potential issues around fairness that we might have seen for regular ad hoc computable forms, and made them available. So at least as of the time of writing the slides, you can go to the HDR UK library and you can download a ready-to-go executable version of that phenotype that has all the benefits that I've been not selling you today. Okay. Again, I'm conscious of time, so I'll just kind of rattle through this. So that's the automatic parsing under the model. We also do we allow humans to also write phenotypes under the Phenoflow model. And this is where the kind of more complex side comes in, where it stops just being codeless and can be more complicated. So as an author, you can submit phenotypes to the library to be used. And again, you then get the thing that you can download, the thing that gets standardized. You can change the implementation, you can plug and play, you can get all the benefits that I've talked about. And again, just to provide a practical example, where has this been done? Well, Oxford University approached us. They said they wanted to standardize this long COVID phenotype that they had. It was quite a complex branching phenotype, and they did this through Phenoflow. And nicely, Phenoflow, and I had a discussion about this yesterday, plugs into Zenodo, which many of you may have heard of. So through GitHub, we then create a DOI for the phenotype. So what Oxford were able to do is reference the phenotype through Phenoflow. So we kind of make ourselves the middleman, which is quite good business, I think. Again, not a product. And then again, just if it's interesting, how do we handle things like branching in a sequential structure is probably a natural question. Well, I understand that CWL can do this natively, so this is very much a best effort thing. But what we do is what we call flattened branches. We store different branches as actual sequential units, And then again, we leverage this kind of the beauty of GitHub, the beauty of version control to store these as submodules within a repository. So again, a really nice benefit there of GitHub. Again, kind of unpicking the architecture. What does the user get from this? If I'm a user, if I'm a researcher that wants to use Phenoflow when it's working, what do I see? Well, if you go on Phenoflow, the website, which I'll put at the end, which will be up soon, I'm sure, you can actually view these standardized phenotypes now. You can see them in all their glory in this sequential structure. You can start to see all the benefits of the clarity with the extra information that you have there, these multi-dimensional descriptions. You can download them as research objects. You can unplug your connector, the connector that's there, and plug in a different one. And critically, you can do that at source, right? So as part of our parsing process, we provide you with some template connectors. We provide you with connectors for OMAP, I2B2 Fire, the list grows. And what you can actually do then is when you come to download your phenotype is you can select which data source you want to use. And what will happen behind the scenes is what Phenoflow will chuck away the first step, what it might have been originally, which might have been something different, like Fire or from disk, and it will plug in your new connector. And in theory, then you can execute that phenotype directly against your data set. And again, we leverage branching here. So again, the beauty of the GitHub approach is that's what branches are naturally for, right? Branches are naturally for different versions of your phenotype. What better to version a phenotype against than the data source? So that's how we naturally map different data sources using the GitHub structure. There we go. Okay. That's the end of me selling the not product Phenoflow to you. So for the final, I guess, 5-10 minutes, if that's okay, Luke, I'm going to be super critical about everything that I've just said. Okay, so I put this under the banner of the future, and I guess the future is to be critical. Okay, because let's be honest, we might get fairer phenotypes. I'm not going to completely undermine my entire argument from this lecture. I do think that Phenoflow gives you fairer phenotypes, better or worse, gives you fairer phenotypes. However, there are some problems, I would say. So we do achieve this connected separation, but is the information we're storing enough? Is it enough to have the ID, to have the description, to have the ontology? Is that enough? Do we need more granularity? Is that enough? As I think I've already said as well, although Phenoflow can in practice accommodate multiple implementation formats, I would say 99% of our phenotypes at the moment are based on code lists. Yeah, so there we're not really fully using the potential of that step-based approach. Because remember, in many cases, it could just be a single step. Do I have this code? Do I not have this code? Again, when I then group, I talked about this idea of introducing artificial complexity. For some people, for some use cases, that might be nice. It might be nice to have this extra layer of insight. For others, it might just be confusing. And again, the connectors approach is good in theory, but as many of you probably experienced, OMOP in one institution probably looked a little bit different from OMOP in another institution. So just building one OMOP connector and hoping that you can just download it and it will work is probably not going to happen. As I've experienced with Luke, we also make some horribly naive assumptions that you can download an entire EDW locally, which I'm told is not possible. So there are limitations. Why am I saying this? And again, I've been trying to say this throughout. Phenoflow is not a product. It's a research object, which I know is a reserved term, which is why it's in air quotes. It's something that's designed to inspire improvement in research. By all means, we can install it, we can use it, we can get some benefits from it, but I really want it to be the catalyst for advancing the field more broadly. I don't want this to be selling you a product that solves everything. I want it to, as I've said here, show problems as much as solve them. And there you go. This is, I said before, Phenoflow is actually down right now. And that's why I simply can't sell it to you as a product. Thank you to our server team. Another nice thing as well, again, with conversations with Luke, I think it's really important to separate Phenoflow the concept from Phenoflow the implementation. Phenoflow was written in 2020. I describe it as my COVID fever dream. And the code is probably not as good as it could be. That doesn't, I don't think, invalidate the idea. But there's definite need there. I call them quite nicely development opportunities, not bugs. There's a need there for improvements. Phenoflow sometimes can fall down because of limitations with the CDBL stack, for example, and there's a definite need to rewrite things. So again, in the spirit of being critical, in the spirit of this not being a product, in the spirit of this being research, I want to emphasize that there is work here to be done. I want to separate the concept from the implementation. And in what I think is my final slide, which I think is good for time, is that despite all these problems, I think there's loads and loads of exciting opportunities and directions for Phenoflow. So more authoring, more parsing obviously means generally more fair phenotypes. I've never, I don't think, undone that benefit that I've been selling you for the talk. I think this does improve fairness. So the more phenotypes we have in Phenoflow, whether it's locally at institutions or whether it's kind of in the public instance, that's going to improve the fairness of these objects. And Phenoflow very much started out as something to support phenotyping, but has evolved in lots of different directions. What we actually found is that Phenoflow has become a really interesting resource for analyzing the space of phenotypes that we have available, right? Because if you've got standardized phenotypes, you can do some data science on those phenotypes. You can understand, for example, I've got 48 diabetes definitions. What's the similarity? What's the difference between them? What does that tell me about the use cases that are out there? How can I automate that process to add extra metadata to my phenotypes that might help people in the future understand how they can be used? And that's exactly what we've been doing. So a little paper there, again, written with some people in this room about initial steps to use Phenoflow, not just as a resource for research, but actually also as a data set in a way. I've been having this dream for a long time with Laura and Luke about this idea called transfer validation. I think we came up with this about 5 years ago. It's still not materialized into anything, which is classic research. But again, this idea that if I've got standardized phenotypes, if I've got commonalities between the steps in different definitions, if one phenotype is validated and one isn't, does that mean that the validation transfers? If it's almost exactly the same logic, maybe. And we branded this transfer validation, but yeah, that's yet to materialize. And one thing that's kind of come out of really exciting discussions this week is, do we need to consolidate Phenoflow in any particular way? Does it, for example, do we need to focus on version control? At the end of the day, is that the most important thing? Do we need version control for phenotypes? We do need it. We absolutely do need version control for phenotypes. But do we need Phenoflow to be that thing? Do we need Phenoflow to be the main thing that supports version control? Should we consolidate Phenoflow so it just works or just supports version control? Should it try and specialize in that area? Because really, again, once you've got that standardized structure, your diffs, your use of Git to understand changes can be a lot more nuanced if you've got this consistent structure. So should we consolidate Phenoflow to focus on version control would be my final thought. So you are welcome to visit Phenoflow itself, maybe next week. There's some nice docs that Luke, I think, has been benefiting from a little bit. You can look at the architecture. I've got a lovely monorepo for those who are fans of monorepo. I've got a quite impressive monorepo, even if I say it myself, with the Phenoflow architecture in there at that link. If you're interested in some of the publications, there should be at that link as well. And drop me an email if you ever want to talk about this stuff. Thank you very much. Of course.
Oh, sure. My rambling question. So when I look at this, I think it's really interesting to think about having a collection of phenotypes in there, all of which have had certain components of them specified. So in terms of thinking of it both as a data source and as reusability, like for instance, one of the things I get excited about is thinking like, wow, if I had this in my lab and we had things defined, then maybe we could take pieces from one and use it across in another, because we know that piece has already worked. So we believe in that. And so in terms of either the UK instantiation or even what you're doing in the research environment, how are you thinking about standardizing those units of the phenotype?
Yeah, we're thinking, I think, apologies if I don't directly answer the question, I'll try with what we've been doing. So we're thinking about it in terms of horizontally. So if I have two phenotypes that are designed for the same condition, what is their horizontal similarity? How can I move those units between the same two phenotypes for diabetes, for example? So that would be one way we're thinking about the connectivity, the modularity, the way we can structure and build phenotypes at kind of this horizontal level. And that's what we kind of explored in this paper. We're also thinking at the vertical level. So if I, for example, have a kind of main diabetes phenotype, and then I have two type 2 diabetes phenotype, is there a relationship there? Can I build something from these super phenotypes, we might call, to these kind of sub phenotypes? And that could work across different conditions as well. So we're thinking kind of along the graph in terms of formalizing, and I hope this does answer your question, formalizing how the modules of the phenotypes can be moved around and how they develop. And this also maps really nicely into version control, because you want to understand the evolution of how am I building the phenotype? Did I derive my type 2 diabetes phenotype from my parent, my super diabetes phenotype? We do a lot of work in provenance as well, which obviously maps really nicely to that too. So, good question, thank you.
Yeah, thanks a lot. And I understand that Phenoflow is mainly focused on EHR data, and especially in connection to code lists. But when I'm thinking about phenotypes, I could imagine that there are other data sources that could also provide additional information to extend the phenotype. I'm talking about maybe unstructured patient-reported outcome data. And I wonder how, in which sense, or to which extent, Phenoflow would be capable of including additional custom modules to also accommodate these kind of additional data sets.
It's a wonderful question. Thank you. Yeah, so this kind of unstructured data is something that we have looked at. So we do have one example phenotype that uses natural language processing. So it doesn't use a non-EHR source. It assumes the unstructured component of the EHR is what is ingested. But we do have existing Phenoflow modules that are designed for NLP. So you can, and it might have been on this screen before, you can at the moment submit, and it's kind of rudimentary, but you can submit keyword-based phenotypes. So keyword list, for example. And what that will do is it will assume unstructured data. And again, quite rudimentary, more of a proof of concept for that element. It will try and find those keywords, again, in the unstructured data of the EHR. And in theory, you could move away from EHR, the nice pluggable approach. You could plug that into anything that you like. And again, one active area for research is machine learning phenotypes. That's what we're kind of talking about with some of the people in the room, and how those can help that kind of unstructured data analysis as well. But it's a wonderful question. Thank you.
Great talk. I was mostly thinking, I was thinking a lot about the connector modules that you mentioned a few times. And I think if, say, tomorrow we wanted to implement Phenoflow here at Northwestern, I think that would be the space that would be the biggest barrier to 100%. Implementing it here. Because you mentioned local flavors of a standard. Northwestern, the EDW in its native format doesn't even use, as far as I know, a standard like OMOP.
Yeah.
So I guess, has there been any thought to automating the process of converting whatever standard, we'll say the Northwestern EDW standard, automating the process of converting it to a connector module?
So I think my first foray into the health informatics space coming from computer science background was this, because that was my first thought was, people are battling all these standards. Let's just convert them all to one standard. I found that really hard, even with the technologies we have now. Maybe things have moved along. Maybe we can do more things with language models now, but I think fundamentally that's really tricky. I'm very happy to explore that. But I think which is potentially too practical dream for this, is to actually imagine that you have a repository of connectors. So we get to a point where, and I don't think it's actually shown on here, but there is another endpoint there, which is actually called add connector. So I'm imagining a point at which, for example, Northwestern have come along, implemented Phenoflow, they've written a kind of connector for their data source. I'm imagining a point at which that happens at scale. So we have a repository of thousands and thousands of connectors. Again, pipe dream, perhaps potentially too big. And what that will do is obviously not solve everyone's implementation case, but you would hope at some point we hit a critical mass, maybe I'm being too optimistic, where you can find a connector that is close enough for your use case so you can limit that work as much as possible. So that is honestly how I've been approaching it, just trying to brute force it almost. But yeah, absolutely. I think there's probably time for me to revisit the idea of converting these standards as an alternative approach, right? We've got language models now, which can be a bit of a dirty word to say sometimes, but they do show promise in terms of these use cases. So yeah, very open to revisiting the idea of automating the mapping rather than just assuming that we've got a connector that might work. No, is that something you've been working on, space you've been working on? No. Okay, no, I think it's a super thought, really like it. Yeah, thank you.
Yeah, Martin, fantastic talk. Thank you. So related to that and the question before, I mean, organizationally, have you interacted much with then some of the standards bodies themselves, like the HL7 community, OMOP community? Do you have like sort of liaisons or work through individuals in those different communities as well?
We've talked a little bit with Odyssey, but I think most people have spoken with Odyssey, so I don't know if I can claim any kind of dedicated work there. But generally, no, but I would be super open to it. Absolutely. I mean, we've had some kind of vague conversations with Odyssey, and they're always very keen and interested in this. I know they have their own phenotype library, so I don't know how they would. I suspect the Odyssey standpoint might be, well, everyone should just use OMOP. So I don't know if there would be any kind of conflict there. But no, super open to talking to people about, or organizations about their standards and how we can connect into them. Spoken a little bit with I2B2 community, who I think are very well represented at AMIA, or were at one point. So we've spoken to a little bit about them, but no, 100% open beyond those initial conversations, beyond those general conversations, to having those kind of interactions, assuming they don't just say, use my standard. You should just have one connector. No, that's super helpful. And if there are connections or contexts you have, that would be superb. Oh, wonderful.
Sure, we have an online
hello
question.
online, wonderful.
I know. I appreciate the Phenoflow phenotyping fair principles. How does this translate into outcomes? Do you have phenotypes of denominator and phenotypes of numerators so we can derive and report quality measures at scale across EHRs?
Wow, great question. I think we are probably too early in the process for that. We do have some very early demonstrators of the utility of this approach. We did a very early demonstrator with clinical trial recruitment where we used phenotypes or Phenoflow phenotypes specifically as a standard to plug in place of proprietary eligibility criteria. So we tried that out in admittedly a kind of toy setting in terms of if I'm recruiting patients for clinical trials, can I plug in my phenotypes? Can I detect individuals with conditions in a kind of more sophisticated way using Phenoflow? And we got some positive results. But generally, I'd say this is the next stage, right? The next stage is thinking about how does all this nice fairness that we have, how does that translate into outcomes beyond these very small scale kind of initial scientific experiments that we've done? I wish I could say we're miles ahead, we've shown tons of impact, but I think we're at a stage where we're kind of still working out exactly what do we want to focus on so that we can move then into that impact. So that was a terrible answer, I'm sorry, but it's something we're thinking about, which is hopefully reassuring. Thank you, online person.
We do have time for one more question if there's one more. Can I ask you a question?
Oh, no, okay.
No, it's not going to be horrible. I had some horrible ones, but I'm not going to ask them.
Oh, please.
So just thinking about the the approach that you take with separating the model of the phenotype from the implementation, just like generally from how we approach developing phenotype algorithms, thinking about them for portability purposes, what do you think?
Was it going to be on me?
I think that was telling me something. But no, what do you think is the right approach of, should we build phenotypes for portability? Should we build them in a way so that they're highly curated and tested on multiple implementations before we roll them out? Or do you think that we should be in a model of building them for a use case, making it fit for purpose and allowing them to adapt, adopt, evolve over time with contributions back?
Yeah, it's a good question. I think Phenoflow kind of takes a bit more of a, I guess, cynical approach to that and says that we're always going to be in this state where all implementations are super ad hoc, super mixed and across the broad, mixed language-wise, and kind of developed by different people, different institutions, different use cases. And the best thing that we can do is kind of get this standard layer on the top. Of course, it would be great to have more of a situation that you describe where we have much more kind of focused. So I guess the answer is A, much more kind of focused curation of these phenotypes that are built and developed and standardized in a particular way. But no, absolutely. Storing things like and when I talk about the data science applications of Phenoflow, fit for purpose, fit for reuse, which I know people in this room are working on, is one of our goals, right? We want to help add a metadata layer, which I might have said already, to these phenotypes that helps us better understand how they can be used, in what use cases they can be used. And again, I appreciate that's a bit cynical in the sense that you're assuming that they've just been developed ad hoc and you need to add that metadata. It's not already there. But yeah, absolutely. In the ideal world, we would engineer these incredible phenotypes where it's clear how they can be reused, where they can be reused. I don't know if we'll ever get there. So there's probably always going to be a place for this abstract layer that we're putting forward. But yeah, absolutely. Bringing up reuse and fit for purpose is very important. It's something that we want to promote and store as metadata through having standardized phenotypes in Phenoflow. So sorry, that was probably a bit of a roundabout answer. No, that was okay. Okay, good. Thank you.
Thank you again, Dr. Chapman.
Thank you so much, everyone. Appreciate it.